Welcome to the annual DefCon convention. This meeting was held in exciting Las Vegas, Nevada from July 9th through the 11th, 1999. This is videotape number 18, Introduction to TCPIP.
Unfortunately, I wasn't able to make copies of these slides. This is going to be kind of a slide-intensive presentation, so if anybody does want a copy of the slides, just grab me anytime during the con. I'll throw them on a floppy for you, or send me an email and I'll get them to you. And for those of you who don't know, I will be doing a brief introduction to TCPIP this morning. What this lecture is going to cover, this lecture is going to be a low-level, it's a low-level overview of TCPIP. This lecture is geared towards novices. This obviously is the newbie track, so it's not going to be a real high-tech presentation. If you do want a high overview of TCPIP, this is the book to get, TCPIP Illustrated, W. Richard Stevens. Buy this book, read it from cover to cover. After you read this one, there's 2 more volumes after this. Excellent book. First off, I want to cover just a little bit of the history of TCPIP, where it all began. Let's see. Essentially, TCPIP started in 1969 when the Advanced Research Project Agency, also known as ARPA, decided to fund some research and development into making basically not really a global network, but they just wanted to start putting all their resources together and make a network that they could put all these resources together and network the computers together and essentially make all their computers work a little bit better together. ARPA's goal wasn't originally the internet as we know it today. That was not their original goal. It was more of a research project. ARPA's goal was to study techniques for providing robust, vendor-independent data communications. So basically, it could put all these different machines together, regardless of operating system, regardless of vendor, and have these machines be able to talk to each other on a network. ARPANET was so successful that many organizations attached to it began to use it on a daily basis. Obviously, it was proved to be a very important resource. People were using it on a daily basis, so it did grow rather rapidly. In 1975, ARPANET converted from an experimental network to an operational network when the Defense Communication Agency, also known as DCA, took control of it. They took full control of it and released it from ARPANET. In 1983, a couple different things happened with TCPIP. The TCPIP protocols were developed as military standards. They were then enforced as military standards. All hosts on the network were then required to be able to use this communication suite to talk to each other. Also in 1983, DARPA funded the implementation of TCPIP in Berkeley or BSD Unix. And also in 1983, the term that we know today as Internet came into common use. Also in 1983, ARPANET split into both the MILNET and also its newer, smaller ARPANET was controlled by 2 bodies at this time. In 1985, the National Science Foundation, or the NSF, created NSFNet and connects it to the Internet. In 1987, NSF created a faster new backbone and a 3-tiered topology that includes both backbone, regional networks, and local networks. So basically, NSFNet was the whole backbone for the entire Internet at this time. And then in 1990, ARPANET passed out of existence. This is probably a lot more memorable for a lot of people. In 1995, NSFNet ceases its role as a primary backbone for the Internet. Basically, that's when it came to be known as what we know as today as the Internet in 1995. So basically, this all can be wrapped up in a nutshell. What has come to be known as the Internet was originally designed and experimented, or it was originally designed as an experimental network that really had no intentions of it growing into the network that it has come to be known as today. The Internet has grown much larger than it was originally intended for, obviously. And also the original networks and agency involved in the creation of the Internet are no longer involved in that process today. They no longer play a role in that. couple of the myths of TCPIP. Contrary to many think, Al Gore did not create the internet. He did not invent the internet. When the internet was funded, Al Gore was only 21 years old. He was a college student. I don't think he had anything to do with it. Okay, now we're going to go into some of the definitions we'll be using. TCP/IP defined. It's a transmission control protocol, internet protocol. Essentially, this is the suite of networking protocols that have been used to construct the global internet. Also referred to as DoD or ARPANET protocol suite. You don't really hear it referred to these days. Sometimes you still may, because they were involved in the early development of this suite. So TCP, defined in a nutshell, is the series of protocols that allows computers to communicate on a network regardless of operating system, regardless of vendor. It doesn't matter what operating system you're running, it doesn't matter what type of computer you're running. As long as you're running a TCP/IP stack, you can still communicate with other computers on that network. Okay, I really hate the OSI model. We're not going to go into that at all with this talk. The thing we are going to talk about is the 4 layers of TCP/IP. This is what's really important. I think when it comes to TCP/IP, the OSI model is not really that important. There's a lot of layers that are not even used in TCP/IP. So let's talk about the 4 layers of TCP/IP. Starting from the bottom, you have the link layer, which is the device driver and interface card, your network interface card. It's as simple as that. Moving on up the stack, we have the network layer, which is typically comprised of IP, ICMP, and IGMP. Moving on up the stack, we have the transport layer, which consists of either TCP or UDP. And at the very top of the stack is our application level. These are the actual applications that the users interact with, such as Telnet, FTP, mail, what have you. A little description of what each layer is comprised of and what it does. The data link layer, this is the very bottom of the stack. This layer includes the device driver in the OS and the corresponding network interface card in the computer. So this is both your network interface card and whatever drivers are required to interface that NIC with your machine. This handles both the hardware details of physically interfaces the network. Moving on up to the network layer. This is also sometimes known as the internet layer. This handles the movement and routing of packets around the network. Moving on up, the third layer, which is the transport layer. This provides a flow of data between 2 hosts for the application layer above. 2 different transport protocols are used at this level. I'll give you a brief description right now. We're going to go a little bit further in depth into those in a few minutes. It uses both TCP and UDP, as I mentioned a few minutes ago. TCP, it's an extremely reliable protocol. It breaks data passed from the application layer above into chunks for the network layer below. It acknowledges every packet that it receives, sets timeouts, and a couple more things which I'll go into in a few more minutes. It's considered to be very reliable to actually establishing a connection with the machine on the other end of the network. The other protocol used at this level is UDP. This is considered to be very unreliable. It sends its packets of data, also known as datagrams, from one host to another. The problem with this is there's no guarantee that those packets that you're sending to that remote host are actually being received by that remote host. And at the very top, we have the application layer. This layer handles the details of the particular application being used. Some of the standard TCP/IP applications include Telnet, FTP, SMTP, and also SNMP. Okay, another definition, encapsulation. What encapsulation is, when an application sends data using TCP/IP, it's sent through each layer in the protocol stack. As it passes through each layer adds its own information to that data by adding its own header and sometimes a footer to that information. The data is then sent as a stream of bits across the network. This is a little graphical representation of exactly how encapsulation works. We start off with our user data. First, it's run through the application layer. Remember, it has to work its way through the top of the stack, go down to the bottom of the stack. Once it runs through the application layer adds on its own application header. The next layer on down is the TCP layer, so obviously that's going to add on its own information. As we can see, it does add on a TCP header. Now this piece of data, or this segment is what's known as a TCP segment. Both your application data and TCP header comprise a TCP segment. Moving on down, the next layer we have is our IP layer. And as you can see, the IP layer adds on its own IP header. And this piece of data is what's known as an IP datagram. It's comprised of your application data, your TCP header, and your IP data. Your IP header. And obviously, the very bottom of the list, or the bottom of our stack, is the link layer, our internet card, or Ethernet card. And the link layer, if you notice, adds both an Ethernet trailer and an Ethernet header. And this piece of data is what's known as an Ethernet frame. This is going to be what's sent across the Ethernet. And that data would now go across the Ethernet, and once it's handled by the other machine, once that piece of data is sent across the wire, what happens is demultiplexing. It's the exact opposite of what happened just a minute ago. When an Ethernet frame is received by a host, it starts its way back up the protocol stack. Each layer then will look at its respective header and its footer, if there was a footer for that layer, and it decides what to do with that data next before it passes on to the next layer up. So when you're sending data from a host, it moves its way down the stack, goes to the host, moves its way back up the stack, and strips all the headers and footers off that are required for that layer, then passes off the application layer and decides what to do with it from there. Okay, now I'm going to talk a little bit about some of the TCPIP networking protocols that are in use today. First, I'm going to talk about IP, some of the features of IP, or the Internet Protocol. IP is the dominant network layer protocol used by the TCPIP suite of protocols. IP defines the rules for packaging network traffic into IP datagrams, and also defines the rules for moving these datagrams across the network. So you can see IP is a very important layer, very important protocol. IP is also responsible for fragmenting the data whenever necessary and to properly reassemble datagrams at the other end. This will make a little more sense in a few more minutes. And this is actually what an IP header looks like. It might be a little bit hard to read because of the lights up here. We couldn't get these lights shut up here. But I'm going to go ahead and describe what each piece of this IP header actually means. Upper left-hand corner, the very first item on there is the version number. This indicates which version of IP is being used, which is typically version 4. Obviously, we're very slowly converging into version 6. There's probably going to be a very slow convergence with that. The next item is the 4-bit header length. This indicates how many 4-byte words are in the actual header. The next item is the 8-bit type of service. I'm not going to go into real big detail on this. TCPIP Illustrator really breaks this down really well and exactly what the different types of service are. But essentially, this indicates the level of service the IP datagram should be assigned. The next item is the 16-bit total length in bytes. This is the actual datagram length. This is the length of the entire datagram, including the header. And the max size of this is 65,535 bytes. The next item is the 16-bit identification. Let's see. This is the actual datagram identification. This uniquely identifies each datagram being sent by a host. You want to have your IP datagrams each having an individual identification, so once they're received by their host, the host knows how to handle that. The next item, we have a couple different flags. There's 3 flag positions there. The first one's not being used. It's represented by the 0. The next flag, DF, is don't fragment, and the next flag is more fragment. This controls how the actual IP datagram is being fragmented as it's being sent across the wire. If you're sending a lot of information across the wire, obviously it's going to have to fragment this information. It can't send it all in one giant chunk. Remember, we have that limitation on how big the actual package can be with this. The next item we're looking at is the fragment offset, or the 13-bit fragment offset. This indicates how many units from the start of the original datagram the current datagram is. Now, this would be used when you're sending quite a bit of data across the wire. That number is going to increase with every packet of data that's being sent across the wire. If you're sending just a very small packet across the wire, your fragment offset is going to be 0. If it's being broken down to, say, 3 packets, it's going to increase with every packet, 1, 2, 3. That way, once it's received at the host, it's going to know how to interpret that data, how to put that data back together, and it's also going to know when it's done receiving data, basically, when it's received the end of that data. The next field is the time to live, or TTL. This is an 8-bit number. This indicates how many routers a datagram may traverse before being dropped, the max TTL being 255. If you don't set a time to live on a packet and you send it out across the wire, let's say at a particular time it can't find its host, it's going to bounce across the internet forever till that host comes up. Can't have that happening on the internet. It could probably cause a lot of problems. The next field is the 8-bit protocol field. This identifies which protocol has handed the IP to data. The next fields are pretty obvious: the 32-bit source IP address, the 32-bit destination IP address. Obviously, it's the IP address which is sourcing this information, and the IP address which is the destination of this information. The next field is the options. This field is not always used. Currently defined options are security and handling restrictions, record route, timestamp, loose source routing, and strict source routing. And these options are rarely used. There's a lot of routers out there on the internet that do not know how to handle these options, so it's very rare that they are used. And obviously, your last field's data is very obvious what that's going to be. That's your data that you're sending to the application, sending to your remote host. Now, this is an actual TCP dump of an IP header, just to give you an example of what it might look like. As you can see at the very top, our version is version 4. That's what's most commonly used on the internet these days. The header length, 20 bytes, that's obvious. The service type, as I said, I'm not really going to go into that today, but that hexadecimal representation represents the level of service that this datagram will be. The next item, datagram length. This is the length of the entire datagram, including the header. It's 40 bytes. Next, we have our unique identification, which we would have for every packet going across the wire. And next, we have our 2 flags, the must fragment and don't fragment. As you can see in this case, must fragment is off, don't fragment is on. That means we're sending a very small packet across the wire. It's only going to be 1 packet going across the wire. Next, fragmentation offset. As I mentioned, this will increase exponentially when you're sending large amounts of data across the wire. In this case, it's 0. It's a very small piece of data we're sending. The next item, time to live, 32. This packet can only traverse 32 routers or 32 hops before its destination, before it's actually dropped. The next item is the encapsulated protocol that's being used in this instance, which is TCP. The next item is the header checksum. This is basically just a bounds checking that the remote host will use to make sure that the data being received is not corrupted in any way. And then we have our source IP address and destination IP address. Those are both obvious. Okay, I just wanted to mention a little bit about the traceroute program. This can be a very useful diagnostic program. especially since there is no guarantee that two connective IP datagrams from the same source to the same destination will take the same route. They usually will, but let's say you're sending data across the wire, a large amount of data going across the wire. If one of those routes should drop, automatically they will be rerouted to that host. That host should still receive all that data. Traceroute is a good program. It's a good tool that can be used to trace the flow of IP datagrams from one host to another. An explanation of how traceroute works. Traceroute sends an IP datagram with a time to live of 1 to the destination host. If you remember a minute ago, I mentioned the time to live is essentially how many routers that packet can traverse before it's going to be dropped. So obviously, once it gets to the first router and is passed to the host, that packet is going to be dropped, is going to be decremented to 0. That packet is going to be dropped by that router. That router is then going to send an ICMP time exceeded back to the host. What happens next? Traceroute then sends another datagram with a time to live of 2. We then find the next IP address of the second router. It'll decrement to 0 once again, be dropped. It'll send back the ICMP time exceeded back to the host, so on and so forth. We'll keep doing this until it eventually does reach the host. And here we just have it's a real simple sample traceroute output. We're tracerouting to victim.com. Traceroute to victim.com, it gives us our IP address. It's going to be a maximum of 30 hops, which is a time to live of 30. And it's sending 40 byte packets. That's the size of the entire packet, including the header, is going to be 40 bytes in this case. As you can see, the first hop is Satan, and it's actually sending 3 packets every time, so we have our average for every packet. 20 milliseconds, 10 milliseconds, and 10 milliseconds. The next hop, which is our actual destination host, is victim. So we can see we have 120 milliseconds for all 3 of those. So for each TTL, 3 datagrams are actually being sent. These values are then recorded in your output. Moving on to TCP, some of the features of TCP. TCP is a transport layer protocol. I mentioned that a little bit earlier. This provides a way to connect hosts across a network reliably. As I mentioned before, TCP is considered to be a very reliable protocol. Actually, TCP provides a virtual circuit between 2 hosts. These hosts are actually connected from one endpoint to another. It's basically a virtual connection between the 2 machines. Communicating hosts are required to acknowledge receipt of network traffic. That way you're guaranteed that information you're being sent to that host is actually being received by that host. If for some reason that host drops in the middle of a transmission, you'd be notified all the information you were sending to that host was not received. Some more features of TCP. TCP packages its data into segments which contain both data and session control information. And since segments traversing a network may arrive out of order, TCP provides proper reassembly of these segments. As I mentioned before, all your packets may not necessarily take the same path. Some of these packets may arrive out of order, so we have to have a means for assembling these packets in the proper order once they arrive at their destination host. This is where sequence numbers come in. Sequence numbers are used to properly reassemble all these packets that are being sent to your host. You can think of the sequence number basically as a 32-bit counter, and it can range anywhere from 0 to 4,294,967,295. So it's a pretty broad range that the sequence number can fall into. And this is just an example of how this is an FTP transfer TCP dump output. As we can see on our first line, we have TCP. It's obviously using FTP, it's telling us. And the sequence number, we're just going to look at the last 4 digits of this, it's 1397. And as you can see, the data payload is 1,460 bytes. So next we increment up 1,460. The sequence number is going to increase by 1,460 for packet 50. It's going to jump up to 2857. Once again, it's 1,460 bytes in this packet. So So our next packet obviously is going to increase by that same amount of number for the sequence number. It increases to 4317. The same thing for packet 52. So essentially, if these packets arrive out of order, the receiving host can still put these packets back into the proper order and acknowledge what this data being sent across the wire is. And one of the other features of TCP, it maximizes performance of a connection by ensuring TCP segments are neither too large or too small. There's a lot of bounds checking to make sure it's not sending too much data. You don't want to send too much data because if that receiving host can't handle that much data, you're going to lose data and you're going to have probably corrupted data being sent across the wire. So everything I've said about TCP can pretty much be wrapped up in a nutshell. It provides a virtual circuit. TCP connections behave like a live two-way communication or a two-way connection. You can basically think about it as just basically a telephone conversation. You're connected from one endpoint to another endpoint. It provides reliable connections. TCP segments are guaranteed to reach their destination, and if for some reason they are not receiving their destination, the user is notified about this. And there's also a lot of stuff put into TCP that provides performance optimization. TCP can modify transmission variables depending on network conditions. For some reason, if a route seems to drop, a route seems to really be lagging, that information will reroute across the network, and essentially it'll still reach the host even if a route does drop. And now we're going to go ahead and take a look at the TCP header and all the fields that are included in the TCP header. The first two items we have, the 16-bit source port number, the 16-bit destination port number. Obviously, this is the IP address of your originating host and your destination host. The next field is your 32-bit sequence number. As I mentioned, the sequence number is a 4-byte number assigned by TCP, starting with a randomly chosen number. Actually, the older operating systems, it wasn't really very random. I'll talk about that in a few minutes. I think Pete's actually going to elaborate on this in the next speech on TCPIP sequence prediction. This number is used to determine how many bytes have been transmitted across the network, so it can properly assemble those packets once they're received. The next field is the 32-bit acknowledgement number. This acknowledgement number acknowledges the last segment sent by the host. We can't have all these packets traversing the network and hitting the host and the host not acknowledging that they're being received. Otherwise, there's no way we're going to have a good connection. There's no way we're going to have a reliable connection going across the wire. The next item is the 4-bit header length. This measures the header length in 4-byte words. The next field is reserved. I'm not going to discuss that. In the next field we have 6 different flags. I'll give you a brief description of what each of those flags mean. These flags may either be turned on or turned off. These flags are used when negotiating and managing a connection. The first flag, which is urge or URG, this indicates the segment being sent is urgent, so you can prioritize the urgency of segments being sent across the wire. The next flag is ACK, or acknowledge, indicates the ACK number and the segment header is valid. The next field is push, PSH. This automatically tells that to pass the data to the application as soon as possible. It puts a precedence on this information to be passed to the application layer ASAP. The next field is RST, or reset. This flag is used to reset a connection. The next flag, which is SYN, synchronize. This synchronizes the numbers used to initiate a connection. I'll talk about initiating a connection in a few minutes. And the last field is FIN. This indicates that the sender is finished sending data. A FIN would be finished, obviously, at the very end of your flow of data, indicating they are no longer sending data. Your receiving host is to know that it has received all its data at that time. The next field is the 16-bit window size. This is the number of bytes the receiving host is willing to accept. This is what's called a sliding window, and this can actually scale depending on what kind of traffic that host is receiving, the max being 65,535 bytes. The The next field, the 16-bit TCP checksum. This is a checksum of the TCP header and data. Once again, this is used by the receiving host to ensure that that data being sent across the wire is not corrupted. The next field is the 16-bit urgent pointer. This is used only if the urgent flag is set, so it sends a precedence on your information going across the wire. The last field are options. The most commonly used options in TCP headers are both MSS, which is maximum segment size. This determines the maximum size segment the sender is willing to receive. So this basically coincides with the 16-bit window size I just discussed a minute ago. And then obviously at the bottom we have our data. Data is not always going to be sent across the wire, as you're going to see in a few minutes. When you're establishing a connection, no data is being sent. You must first establish that virtual connection before any data can be sent across the wire. So essentially this segment of the TCP, this portion of the TCP segment is optional. And also jumping back to the synchronized numbers, I was talking about how the host synchronized, they use these numbers to determine how much data is being sent across the wire, and it's also used to properly assemble these packets. On older systems, this number, when you first bootstrap the system, this number is set at 1. Every second it increases by 128,000, and every connection it would increase by 64,000. That's why in a lot of older systems it was a lot easier for people to try and predict TCP sequence numbers. These days on current TCPIP stacks, this number is generated randomly, so it's not quite so easy to try and hijack a connection with that. I think Pete's going to be elaborating on that a little bit more in the next segment. This is an actual TCP dump of a TCP header, give you an idea of what it looks like. Our source port is 22, it's a well-known port, SSH. Destination port's 1,714, it's an unknown port, it's an FRMO port. The sequence number, our acknowledgement number, the header length, which is 20 bytes, is telling us there's no data in this payload. And our flags, the urgent flag is turned off, the acknowledge flag is turned on, the push flag is turned off, reset flag is turned off, the synchronized flag is turned off because we're not establishing a connection, we're already connected to this host, and the fin flag is turned off. The window advertisements, 32,736 bytes. This is how many bytes of data our remote host is willing to accept at that particular time. We also have our checksum that is used by the receiving host to ensure this data being sent across the wire is not being corrupted, and our urgent pointer is being set to 0 because of the fact that the urgent flag is off. It's just a little graphical representation of what actually happens when you establish a three-way connection or a TCP connection to a remote host. It's what's known as a three-way handshake. Initially, the client will send a SYN packet to the server with an ISN of X. We'll say it's X right now. It's not really important what number that is. The server is then going to reply with a SYN. It's going to set its own ISN as Y. And it's also going to acknowledge the client's ISN by adding 1 to it. So it would be X plus 1 in that case. The client then sends back another acknowledge with the server's ISN, which would be Y plus 1. Once this happens, we have a full connection established. Data connection will be sent across the wire at this time. And this is a packet dump showing exactly what it looks like when this three-way handshake is being established. As you can see, we're connecting from TC port 24,616 to an FTP port. We have our sequence number. I'll scope off the last four. That's 1,453. The requesting client sends a SYN or a synchronized segment, specifying the port number of the server it wishes to connect to and the client's ISN or initial sequence number. Part 2 of the handshake. The server responds with a SYN segment, including the server's own ISN, which is in blue, the last four being 5737. An acknowledgement is also sent with the client's ISN plus 1. So as you can see, that did increase by 1. It's at 1454 now. It was originally at 1453 when we first initiated this connection. And the last part of the three-way handshake, the client acknowledges the server's SYN and sends an ACK segment with the server's ISN plus 1, which is the number in the blue. As you can see, that did increase by 1. It's now at 5738, whereas before with the last packet, it was 5737. All right, if there's any questions, you can feel free to ask them at any time or save them until the end. Moving on to UDP, User Datagram Protocol. I mentioned before, UDP is also another transport layer protocol such as TCP. UDP does not use the benefits of error detection, error correction, handshaking, or verification of delivery like TCP. It provides a connectionless delivery system between two hosts, and because of the fact that there's no error checking, error correction, it doesn't ensure that your packets are receiving the host. UDP does have very low overhead. It's typically only used for very simple applications such as TFTP. If you have a real intensive application, you're not going to want to use UDP because there's no guarantee that this information being sent across the wire is actually receiving its host. With an intensive application, you want to guarantee that the information is properly going across the wire. Now we'll take a look at all the fields in the UDP header. As you can see, it's a very small header because of the fact that it doesn't have a lot of these error correction bounds checking like the other information did. At the very top, the first two areas of the UDP header, the 16-bit source port number, 16-bit destination port number, those are both pretty obvious. The 16-bit UDP length. This indicates the length of the entire UDP datagram, including the header. Next, we have the 16-bit UDP checksum. This is a checksum of the entire UDP datagram. Once again, this is used by the receiving host to ensure that data being sent across the wire is not being corrupted. And the last field is our data. It's obvious what that's going to be. It's our data we're sending to the application on the remote machine. Yes? He was asking, he said UDP does not do error detection. It's not actually doing error detection, it's just ensuring that that packet is properly formed once it's received the host. Let's say that packet does hit the host and it says there's something wrong with this packet, it's not going to let you know if there was something wrong with it. Right. And next we'll take, this is an actual TCP dump of a UDP header, see what it actually looks like. Our source port's 2167. This once again is an ephemeral port that the user is interacting with. The destination port's 53, domain service, domain name service port. It's a DNS request. Datagram length is 37 bytes, 8 of which is the header, and 29 of which is the actual data being sent. And then we have our checksum. That actually pretty much wraps up my speech. There's a couple references I have in my slides. As I mentioned before, TCPIP Illustrated Volume 1, excellent resource. It's kind of difficult to get into at first, but the more you read up on it, the easier it does seem to get. Also, TCPIP Network Administration is one of O'Reilly's books, written by Craig Hunt, is a pretty decent book also. Like I said before, if anyone does want a copy of these slides, you can drop me an email. It's punkis@attrition.org. I'll be glad to send you a copy of these. And let's see. Also having the references, the TCPIP fact, the frequently asked questions, is broken down into two parts. There's a URL for that I could give to you. I'm not going to read it. And also TCP Show. TCP Show is a really good program. If you're trying to learn about TCPIP, I really recommend this program. It's a program that's used in conjunction with TCP dump. TCP Show essentially reads a TCP dump save file, provides a reasonably complete decode of Ethernet, ARP, RARP, IP, ICMP, UDP, and TCP headers and packets that match the Boolean expression. All the dumps that I showed on the screen in this presentation were done using the program TCP Show. I don't know how familiar people in here are with TCP dump, but it doesn't really provide an output that's real easy to determine what's going on with that information. So both TCP Show and TCP dump used in conjunction with each other are excellent tools to examine exactly what's going on with TCP/IP. Hold on. Email address is on the screen. Is Punkis, Punkis, @attrition.org. For those of you who weren't in here before, who in here is familiar with attrition, just out of curiosity? A couple people. Just so everyone gets a heads up, we are going to be changing the focus on attrition. There are going to be a lot of changes coming up in the near future on that, so keep your eyes on that. We are going toward a more technical content with that. So we are changing our focus a little bit on that. We're not dumping anything. We are ending a couple things. We're going to finish on a couple things. There's a couple things that we feel we don't need to pursue anymore. We think we've proven our point on a couple of the issues that we've been making. The errata section will not go away. So, reporters. Okay, is there any other questions? Yes. Yes. What's that?
Does that only do Ethernet?
He was asking if TCP Show will do both Ethernet and token ring. Is that correct? To my knowledge, it does Ethernet only.
Do you know if it's included a Bluetooth token ring?
I don't myself, no. Why doesn't it increase by 1? Pete's going to be talking about this with the TCP/IP vulnerabilities. If it increases by 1, it's going to be very easily for an attacker can send basically a fake packet coming from wherever he wants to. When they're receiving host is going to send back an acknowledgement number, you're going to know what the next number should be in that sequence. So it'd be very easy to hijack a connection with that. It's the older TCP/IP stacks, every second they increase 128,000. Every connection estimated increased by 64,000. So with a little bit of luck on older systems, it was a little bit easier to actually hijack a TCP session. Yes? UDP rarely is used anymore. I mean, what's used, TFTP is one of the really only stock applications that come with most systems that uses UDP anymore. Like I said before, it's just used for if you have a very non-crucial application, I guess I could say, where it's not really totally important that the data being sent across the wire is being acknowledged. If you're just using a system where you want a very low overhead, UDP would be a good time to use that. I didn't hear all what you're saying. So. I really don't think, he asked about UDP being used with video transmissions. I doubt you'd really actually want to, because you'd probably be dropping a lot of frames not actually knowing it. So, typically, video applications being sent across the internet are pretty intensive, and you'll want to use something like TCP to send information. Yeah, it would be obvious, but for instance, if you have some kind of service where people are paying for this information and you're dropping frames, and obviously your video output's not going to look very good. I mean, that'd be kind of up to the user that's pushing that information across the wire. True. The checksum, I'm not going to really go into that. That's a little more high level. It's actually a little bit above what I'm working on right now. I can't answer that. It's a hexadecimal number that's generated by examining the contents of the payload. The same thing's done once it's received by its receiving host and to ensure that the data is being received properly. Any other questions? Comments? Death threats? I can't hear you. What about it? There's not a time to live? Okay. He was asking what could be a potential problem with sending information across the wire without a time to live. Obviously, if I'm sending information to a host on the internet that's not actually up at that time, this information is going to be bouncing across the internet forever. Let's say that host never comes back up. This internet's always going to be bouncing across the internet. So you're going to cause a lot of overhead problems, obviously. Hosts are dropping every day. So using the TTL, they will. Without the TCL, they will not. Well, the TTL cannot be set above 255, so there is an upper limit on that. And back? That's not going to be enough? What do you think about that? His question is, with the exponential increase in the internet, more and more routers being pushed out there, is there ever going to be a time when a time to live of 255 is not enough?
At this point, no. If you have that many hops, it's a bad network topology design.
You know, typically, if you trace route a host, even if you're trace routing it to the other side of the world, you're probably not going to have more than 20 or 30 hops. I've never done a trace route where I've had probably more than 40 hops. So I think actually 255 is very reasonable.
Average about 8 to 16.
Right. Yes. Right. It's being done automatically by trace route. There are modifications. I think actually Route has written one where you can increase where that can be changed. But that's the default that it sets it as, is 30. That's why sometimes if you're doing a trace route and you'll get your first 3 lines of information, then you'll get a couple rows of asterisks, it's exceeding its time to live, that those packets are being dropped. Any other questions? Actually, it depends on who you ask about it. It's some people say it's one, some people say it's the other. Typically, it's just how many hops. Yes. The urgency set automatically unless you actually build a program where you're constructing your own packets. It's set automatically. Read TCPIP volumes 1 through 3 and learn how to program in C. Route does make a program called LibNet. I'm not sure what his site even is these days. I don't even know if it's up. It's LIBNET, and I know...
It's a C function library that does all the nasty math for you. Packetfactory.com, I believe, is the new URL for that. And actually, they're supposed to be releasing a newer and bigger version of that in the real near future, I believe. Any other questions? Okay,